We're in section 5.4, applying definite integration, distribution wealth, and average value. The first thing that we have here listed is the total area between a curve and the x-intercept. So if you look, we have a positive area, and a positive area is where a function is greater than 0 on that interval, so you'll notice that it is above the x-axis, whereas we have a negative area, which is when a function is less than 0 for an interval, and that is below the x-axis. The x-intercepts are where the area will change from positive to negative or negative to positive. So to find the total area from this picture that we're given here, we're going to have to take our positive area and add together the opposite of the negative area, or subtract away the negative area. So finding area, in summary, to find the area bounded by f of x with x equals to a and x equals b, and the x-axis, we're going to use the following steps. First thing is to sketch, and that's really key just so we get an understanding of what the graph looks like. 2 says find any x-intercepts of f of x on that interval. These divide the total region into subregions. So again, remember to find your x-intercepts, you set y equal to 0. 3 says the definite integral will be positive for subregions above the x-axis and negative for subregions below the x-axis. Use separate integrals to find the positive areas of each subregion. 4 then says the total area is the sum of all these areas. Again, each area would have to be represented with a positive. The example at the top of the next page says use the definite integral to find the area between the x-axis and f of x over the indicated interval. Check first to see if the graph crosses the x-axis on the given interval. So the first one that we have is f of x equals 4x minus 32 over the interval from 5 to 10. And so I'm going to go ahead and sketch this graph to see what it's doing. But if you notice, if you substitute in 5, we have 20 minus 32, which would be a negative value. And when we have 10 substituted in, we have 4x minus 32, which is a positive value, so I know that it's going to be crossing the x-axis. So putting on 10 here. Again, if I substitute in 5, I get 20 minus 32, and that would give me negative 12. So I'll just do a rough sketch here. And to find my x-intercept, since we do know that this is going to cross, we're going to set y equal to 0. So we have 0 equals 4x minus 32, or 32 equals 4x, or x is equal to 8. So I know that it's going to cross at 8 for our x value. And then substituting in 10, we know that we get a positive value of 8. Since we get 40, 4 times 10 is 40 minus 32. So connecting these to make my linear line, I need to find the area of the first region, which is going to be a negative region, and then also find the area of my second region, which is up above. So I'm going to go ahead and look at the first region, which is going to be this positive region. And for our first region, I'm going to be integrating my function, which is 4x minus 32, with respect to x. And the x values that I'm going to be integrating from are going to go from 8 to 10. And so with this is going to be my positive region. And then I'm going to subtract away the negative region. And that negative region I'll call region 2 here, which is below the x-axis. And this is going to go from 5 to 8 of the same function. So from here, integrating 4x minus 32, we get 4x squared over 2 minus 32x, evaluated from x equals 8 to 10, then minus Same thing when we integrate here, 4x squared over 2 minus 32x, evaluated from x equals 5 to 8. You can clean this up a little bit and just call this a 2x squared, but substituting in the 10, and then subtracting away and substituting in 8. And then I can also subtract and then substitute in 8. I'm going to have 2 times 8 squared minus 32 times 8 minus, and then substitute in 5. So we have 2 times 5 squared minus 32 times 5. So from here, working out 2 times 10 squared minus 32 times 10, we get negative 120 minus, and then substituting in 8, we get negative 128. So we'll subtract those. Minus, and then substituting 8 again, we get the negative 128. Minus, and then substituting in 5, we get negative 110. And so then working this out, we arrive at 26. The example, part B, says f of x equals 9 minus x squared, and the interval we're talking about goes from 0 to 6. And so the first thing we're going to do is graph this, but note that if you were to substitute in 0, you would have a positive 9. And then substituting in 6, you'd have 9 minus 36. And so that would be a negative value, so we know that this is a cross, and we would have an x-intercept. And so again, to find our x-intercept, we set y equal to 0. I'm going to use this to make my graph. So 0 equals 9 minus x squared, or x squared equals 9. Taking the square root, we get x equals plus or minus 3. But our interval is only positive values, so going from x equals 0 to 6. And so this means that the only value that we have would be x equals 3 for an x-intercept. So graphing this, we do know we have a parabola. And at 0, again, we have positive 9. And then 9 minus 36 would be negative 27. So rough sketch here. We also know that it does cross the x-axis at positive 3. And so from here, we have two areas. We have a positive area, which is above. I'll call that 1. And the negative area, which is between the x-axis and our graph, which is over on the right-hand side, and I'll call that area 2. So in order to find the total area here, I'm going to do the positive area minus the negative area. And so our positive area, which again is that top area, negative area on the bottom, is going to be the integral of our function, which is 9 minus x squared dx. And we're going to be integrating that from 0 to 3. Minus, and then our negative area is going to be same function, 9 minus x squared dx, but this time we're going to be integrating from 3 to 6. So from here, if we integrate this, we get 9x minus 1/3 x cubed. And evaluating the first one from 0 to 3 minus 9x minus 1/3 x cubed. And evaluating this from x equals 3 to 6. So first substituting in 3, and we arrive at 9 times 3 minus 1/3 times 3 cubed. Substituting in 0, I know it's just going to equal 0, so I'm going to put 0 there. Minus, and then substituting in 6, we have 9 times 6 minus 1/3 times 6 cubed. Then minus, substituting in 3, we have 9 times 3 minus 1/3 times 3 cubed. So from here, we have 18 minus 0 minus negative 18 minus 18. So working this out, you get 54. The example right below says, a small company found that the rate of profit in thousands of dollars after 2 years of an operation is given by, and we're given a function there, it's p prime of t equals t plus 1 times t squared plus 2t plus 3 raised to the 1/3 power. Find the total profit in the first 3 years. So in order to find the total profit in the first 3 years, since we're dealing with a derivative function here, I need to integrate this. So to integrate this, I have integral of t plus 1 times t squared plus 2t plus 3 raised to the 1/3 power. And it does say for the first 3 years. And so since we're going to be integrating this with respect to time, evaluate this from 0 to 3. And so now integrating this, I'm going to let u equal my inside function, since I have an inside function and also an outside function. The inside function is going to be the part that's raised to the exponent. So I'm going to let u equal t squared plus 2t plus 3. And in doing this, I'm going to have du equals 2t plus 2 dt. Or we can say that dt is equal to du over, and I'm going to factor out that 2, so 2 times t plus 1. So from here, this is now going to be the integral of t plus 1 times u to the 1/3, and then instead of dt, we're going to have du over 2 times t plus 1. The t plus 1s are going to reduce out, and we're left over with just the integral of u to the 1/3 du. Now, one thing to note is that these limits of integration that we had, that we're going from 0 to 3, correspond with dt. And now we're in terms of u, so I cannot write 0 and 3 as my limits of integration. I need to change those. So the easiest thing to do is look back up here, draw a couple arrows from what you let u equal. And I know that the upper limit of integration, t was equal to 3. So u is equal to 3 squared plus 2 times 3 plus 3. And so I have 9 plus 6 plus 3, or 18. And that's going to be my new limit of integration now that I have u's. The new lower limit of integration, I need to substitute in t is 0. So I have u equals 0 squared plus 2 times 0 plus 3. So u is going to be equal to 3. And that's my new lower limit of integration. We also had that 1/2 out in front that I forgot to add in, that we need to add in. So from here you have a 1/2 times, we're going to add 1 to our exponent, so we get 4 over 3. You can either divide by this or multiply by the reciprocal, which would be 3/4. And we'll evaluate this from u is equal to 3 to 18. So from here, this simplifies to 3 over 8, u to the 4/3, and again evaluating this from u equals 3 to 18. So substituting in 18, we get 3/8, 18 to the 4/3, minus 3/8, 3 to the 4/3, and you can substitute that in on your calculator, and you get 16.067, and this is going to be our profit. So this is profit, and the units that we're dealing with are in thousands of dollars, so thousands of dollars. So 16.067 thousands of dollars, or you can just times it by 1,000 and say this is equivalent to $16,067. The problem continues on to the next page. In part B, it says find the profit in the fourth year of operation. So since we're dealing with the fourth year of operation, that's going to be the integral of our function, which again is t plus 1 times t squared plus 2t plus 3 dt. But since it's only the fourth year of operation, that would start 3 and go to 4. And so we know we already did the work. So I'll put some dots here. And we know that this simplified our integral that we were able to arrive at is 3/8 u to the 4/3 from up above. And again, if you wanted to, you could rework it out, but we already know what it equals. But this time we're evaluating it from u equals 3 to u equals 4. So substituting these values in, we get 3/8 4 to the 4/3 minus 3/8 3 to the 4/3. And substituting this in on our calculator, we get 12.685. And again, it's in thousands of dollars, which is the same thing as $12,685. Part C says what is happening to the annual profit over the long run. So if you think about it, the first 3 years it was 16,000, and then that fourth year was 12,000, so it's increasing per year. So it is increasing. The next thing that we have is the area between two curves. The area between two curves, if f of x is greater than or equal to g of x on the interval from a to b, then the area between the curves f of x and g of x from x equals a to x equals b is given by the integral from a to b of f of x minus g of x. Notice that this is the larger function minus the smaller one, or if we want to think about it as the top minus the bottom function. So again, the larger minus the smaller. And so what this shows down below is to find this area in between these two curves. We're going to take the area of the top function between the function and the x-axis and subtract away the bottom function, the area between that bottom function and the x-axis, and that would give us that in-between area. And so we have an example right below that says find the area bounded by f of x equals 4 minus x squared and g of x equals x plus 2 from x equals 2 to x equals 1. So from here I need to sketch this graph to see exactly what I'm dealing with. Also, it does say bounded. So I know that these graphs are going to intersect, and if you're not sure where they intersect, we can set them equal to each other. But I'm just going to go ahead and graph them first to see if I get a better understanding of what these graphs look like. And again, we're graphing this between x equals -2 and +1. And so the first graph that I have is a parabola, and if I were to substitute in -2, I get 4 minus 4, or 0. And then if I were to substitute in, say, 0, we get 4. And then substituting in 1, we get 3. And so our graph is that parabola. The second graph that we have is g of x. And g of x is x plus 2. So again, substituting these values in, -2 would be 0. If you substitute in 0, you get +2. And if you substitute in 1, you get 3. So this would be that straight line. I'm going to go ahead and label these. The top one that we did was f of x, and the bottom one is g of x. And we are looking for this area in between. So in order to do this, we need to set up our integral. And so our integral that we're integrating from, the x values go from -2 to +1, since that is bounding those curves together. It's going to be the top function, which is 4 minus x squared, minus that bottom function, which is x plus 2. And we're integrating with respect to x. so dx. From here, I can distribute my negative and combine my like terms. So this is going to be equal to the integral from -2 to 1 of, and we have -x squared minus x, and then combining these like terms, I have 4 and then -2, so that would equal +2 dx. And so from here we can integrate this and we get -1/3 x cubed minus 1/2 x squared plus 2x. And we're evaluating this from x equals -2 to 1. First, substituting in 1, we get -1/3 minus 1/2 plus 2 minus, and then substituting -2, a little bit more work here, but -1/3 -2 to the third minus 1/2 -2 squared plus 2 times -2. And then substituting this all into our calculator, we get an area of 9/2. The example at the top of the next page, I'm going to go ahead and circle, and we'll look at that one together in class. Right below that, it says net excess profit. And this says suppose an investment will generate a profit of P1T, and a second investment will generate a profit of P2T. The derivatives of each of these profit functions is then respective rates of profitability. Then if the derivative of the second one is greater than or equal to the derivative of the first one, those rates, over the next n years, then E of t is going to be equal to P2 of t minus P1 of t, represents the excess profit of plan 2 over plan 1 at time t. Then the net excess profit would be NE, which is E of n minus E of 0. So that is given down below in the formula. So we have an example right below that says suppose that t years from now, one investment will be generating profit at a rate of P1 prime of t is equal to 50 plus t squared $100 per year, while a second investment will be generating a profit at the rate of P2 prime of t equals 200 plus 5t $100 per year. Part A says how many years does the rate of profitability of the second investment exceed that of the first. So in order to do this, the first thing we need to do is figure out where they're equal to one another. And so since we're talking about the exceeding the rates, I know I'm going to be setting those derivatives of the first investment equal to the derivative of that second investment for those rates. So the first one is 50 plus t squared, and that second rate is going to be 200 plus 5t. From here, I'm going to move everything to one side of the equation. And so we have t squared minus 5t, and then subtracting the 200, we get negative 150. From here, we can factor this. The two numbers that multiply to 150 and add to 5 are going to be a 10 and 15, with the 15 being negative. And so we have 10, and we also have negative 15. Setting each of these factors equal to 0, we get t is equal to negative 10, and t is equal to positive 15. So t is in years, and so we know that time is not allowed to be negative. And so we know that they will be equal in 15 years. So for how many years does the rate of profitability of the second investment exceed that of the first? So we'll say for 15 years. Part B is on the next page, and this says compute the net excess profit for the time period determined in Part A. Interpret the net excess profit as an area. So E of t, the first thing we need is to compute that, is going to be P2 of t minus P1 of t. And so that means that the derivative would be equal to P2 prime of t minus the derivative of P1 at t. And we're dealing with this over the period of time from 0 to 15. And so then our net x's from the formula up above is going to be equal to e of 15 minus e of 0, which is going to be the integral from 0 to 15 of e of t dt. And again, that's from that formula that we had listed up above. And then we also know that from here we have the integral from 0 to 15 of, and so we know from up above e of t is equal to p2 of t minus p1 of t dt. And then we also know that p2 of t is equal to 200 plus 5t minus p1 of t is going to be 50 plus t squared dt. So from here we can simplify our integrand. We're going to have from 0 to 15 of, we have 150 plus 5t minus t squared, and integrating with respect to t. And so integrating this, we get 150t plus 5 over 2t squared minus 1/3 t cubed. And we're going to be evaluating this from t equals 0 to 15. And so the first thing we need to substitute in is going to be 15. So we have 150 times 15 plus 5 over 2 times 15 squared minus 1/3 times 15 cubed. And then substituting in 0, that would just be 0. So I'll put a 0 there for that. And then substituting this all in on your calculator, we get 1,687.50. And looking back at the units that we had up here, you'll notice that we are dealing with hundred of dollars. And so for this we have 1,687.50 hundred of dollars. Or we can multiply by 100 and we get $168,750. And this is going to be our net excess profit. And so again, this is the area between profitability. So right below this, we have the average value of n numbers you would find by adding up all those numbers and dividing by n. The average value of a function f on a to b can be defined in a similar manner, dividing the interval a to b into n subintervals, each with a width of delta x. Then choose an x value, x of I, in each subinterval and find f of x of I, the average function value for the subintervals, and the given choice of xi is going to be, so you're adding up all those y values and dividing by n. And since delta x is going to be b minus a over n like we saw earlier, if we multiplied that to the top and to the bottom, we can rewrite this and notice that we have 1 over b minus a, the sum of f of x of I, and then b minus a over n is the same thing as just delta x. And then from there, if we take the limit as x approaches infinity, we saw earlier we can rewrite that as a integral. And so we have 1 over b minus a, the integral from a to b of f of x dx. And so definitely a formula to know is going to be that average value of a function. The graph right below has the rectangle that has the same area as the shaded region under the curve is going to be found at that average value. So the height of the horizontal line is the average value of that function. So you can imagine that line cutting that shaded part of the graph would be able to fill in that missing part that's down below that line. So at the top of the next page, we have a couple examples. The first one says find the average value of a function f of x equals 2 minus 3x squared on the interval from 1 to 3. And so this is our a value and this is our b value. And the formula was given before, and we had average value is going to be the 1 over b minus a times the integral from a to b of our function f of x dx. And so setting it up for this problem, I have 1 over 3 minus 1 times the integral from 1 to 3 of f of x, which is defined as 2 minus 3x squared dx. And then simplifying this, we're going to get 1 over 2, and we can integrate this, so we get 2x minus 3 times 1/3 x cubed. And again, evaluating this from x equals 1 to 3. So we can simplify this a little bit. First of all, the 3's would reduce here. And we have 1/2 times 2x minus x to the third. And again, evaluating from x equals 1 to 3. So first value we're going to substitute in is 3. So we have 1/2 times 2 times 3 minus 3 cubed minus 1/2 times 2 times 1 minus 1 cubed. And substituting this all in on our calculator, we get a value of -11. So the example below this one says find the average value. This time our function is f of x equals x plus the square root of x on the interval from 1 to 4. So a is 1, b is 4. And so the average value function is listed up above. I'll give that a star. So for this problem, we're going to have v equals 1 over 4 minus 1 times the integral from 1 to 4 of f of x, which is going to be x plus the square root of x dx. From here, I'm going to simplify this a little bit and rewrite the square root as a power of 1/2. So we get 1/3 times the integral from 1 to 4 of x plus x to the 1/2. And so integrating this, we get 1/3 times 1/2 x squared plus, and then adding 1 to our exponent, we get x to the 3 over 2, and multiplying by that reciprocal of 2/3. And evaluating this from x equals 1 to 4. From here, I'm going to distribute that 1/3 just to kind of clean it up a little bit. So I get 1 over 6x squared plus 2 over 9 x to 3 over 2, and evaluating this whole thing from x equals 1 to 4. So again, using that fundamental theorem of calculus, I'm going to substitute in the upper limit first. So I have 1/6 times 4 squared plus 2 over 9 times 4 to the 3 over 2 minus, and then substituting in 1, we get 1/6 plus 2/9. So from here, working this out, I'm going to write my answer as a fraction, and that would be 73 over 18. The next two examples, I'm going to go ahead and circle, and we'll look at both of these together in class.